Okay, welcome back. Today we're going to look at a slight improvement to Minimax. I hope you were able to understand the Minimax algorithm. It's absolutely important that you can understand that because we're going to move on to a slightly more difficult algorithm today. So, as we discussed the last time, the problem that Minimax has is that the number of game states that it has to examine is exponential in the depth, right? B to the M, which is depth first search. And we kind of just mentioned the idea of pruning, which is can we ignore parts of the search tree or the game tree that actually is not going to make any difference to the final choice? Meaning we reduce the number of evaluations and branching. So the calculation of optimal decision can actually take into account what we already know. So let's say we start the search and we do a DFS, and as we go along we kind of have some values, right? We've computed some values that A can have, some value that B that Max can have and Min can have, and can those values help us then to traverse the tree, and then those values can give us a clue whether taking that move is whether taking the next move is even worth taking at all, because maybe that move has a bad effect for one of the players. So this is the idea of alpha beta pruning, which we will introduce in a bit. But first, let's look again at this example simple two-ply game that we looked at earlier in the last lecture. And let's see if there are some nodes that we don't have to evaluate. So here we have the game tree, which is a simple tree where A starts to play, just takes one move. Sorry, that Max starts to play, and then Min plays another move. And this is the utility that A gets at the end, right? And we apply the Minimax algorithm onto the root, which is A, which is basically going to call max of, min, because the max of min of B, which is 3, 12, and 8, followed by the min of 2, in this case, x and y, and min of 14, 5, and 2. And we decided to call these x and y for now. Okay, let's see what happens. So initially, the search goes all the way down to 3, and 3 is returned, and then it goes to 12, it goes to 8, and min is going to compute that 3 is the minimum for that, and that value is passed back. So now Max already has this value 3 up here, right, waiting. So it knows that it's going to compute the max of a bunch of numbers, but the first number that it has is 3. So that's actually quite useful information. Let's see what happens now. So Max says, okay, I'm going to have to take the maximum out of a bunch of numbers, first of which is 3. Now it goes down to this path, following Minimax, and it gets to 2. And 2 comes up here. And as you know, C is supposed to get the minimum of a bunch of numbers. The first one is 2. So what this tells us is that the minimum of any bunch of numbers, if one of them is actually 2, meaning C is going to have a value of 2 at most, right? Because if this is 4 and this is 6, then, the minimum of that is going to be 2. So basically, it doesn't matter what those two numbers are. We just say x and y in this case. C is going to have the value of 2 or less. Okay, basically C is not going to have anything better than 2. We know that for sure. So if C has values like 7 or 1, or 70 and 1, or 700 and 7,000, okay, it's going to be 2. But if it's 7 and 1, then C is going to have the value 1. basically C is not going to have anything better than 2, anything higher than 2, sorry. Now, how is that going to affect A up here? Because A is now going to take a maximum out of a bunch of numbers. And if it knows that C is going to, return at most 2, right? It's not going to return anything bigger than 2, then what's the point of even adding this number here? Because it's not going to affect the maximum function here, right? So whenever this min function here seems to be smaller than what is already, up here, what you're saying is, oh, I can now just completely ignore this part here. I'm not going to go there because I don't have to, right? Because I already know that this node here has the value 2, and therefore whatever I'm going to return up here is going to be 2 or less, and that's not going to help, that's not going to improve this max. So that's why you don't have to expand these nodes here. You just forget about them. And this is the idea behind alpha beta pruning. So you need to really understand the intuition behind it. But let's say, so that is for this node. And let's say A then goes to the other child node, okay, and it sees that this is 14. So now we're going to see, can we prune any more of the tree? So 14 comes back, and D knows that it has to get a bunch of minimum starting from 14. So it's going to be at most 14. It's not going to be more than 14. However, for A, it cannot say that it has to stop because 14 can be a candidate for your max, right? If 14 ever gets in here, then that's going to obviously affect the results of this max value. So if 14 goes here, then the maximum of 3 and 14 is going to be 14. So we cannot prune this part. We have to keep going. And so we keep going and we get 5. And that means D is going to compute, a minimum of 14 and 5. So now 5 becomes the value. However, 5 is still kind of, a candidate that can go here. And if you have the max between 3 and 5 and a bunch of other numbers, it will affect because 5 could be the maximum number. So we cannot rule out this. And finally we go to 2, and then we realize, okay, the minimum of this node is 2. Okay, but we only got the 2 at the end. And now we realize that, 2 is, it doesn't have to be brought back up. Okay, but we couldn't avoid these computations here simply because these values, were going to affect the maximum calculation in case they were sent back. So 2 became the value. However, 2 is not going to affect the maximum function here. So 2 is actually not going to change what you already have. However, if you had like a number like 1 here, if let's say you started off with 1 here, then, it's obvious that you will be here with a bunch of numbers starting with minimum 1, and that, is immediately you can tell the search to stop, and you can prune all of this because the minimum of a bunch of numbers with 1 in it that is not going to be bigger than 1. And if you're going to pass that number back, which is 1 or less, that's not going to affect this maximum. So that's the idea, and that's the intuition behind alpha beta, and you need to make sure that you understand this at the very least. Okay? And this is why we want to use these pruning so that we don't have to go to places where we already know it's not going to, make any difference to our decision. In fact, going there is going to be worse in terms of computation. And that is the main idea for alpha beta pruning. If a player has a choice to move to node n that is for consideration. However, if there is already a better choice of value for that player from previously processed nodes, then you can ignore n, okay, exactly as we saw before this. And we have two variables, okay, and that's where this name alpha beta comes from. We have alpha, which is actually tied to the max player, okay. Alpha is a maximizer. It is actually concerned with what is the minimum that I can take as max, okay? The reason it's thinking like this is because it has to think in the worst case scenario, right? Because if you start off, you always have to think in the worst case scenario because you're thinking your opponent is going to play in the most optimal way, and therefore you always have to think in worst case scenario. So alpha is tied to the first player, or who is, max, and beta on the other hand is the second player who is trying to minimize. And this, in this player's thinking, it is thinking, okay, what is the maximum that I have to give, okay, again in the worst case scenario. And don't worry too much about this for now, but it will come apparent once you've understood the algorithm. So just understand that there are two parameters, alpha and beta. Alpha is tied to the maximizer and beta is tied to the minimizer. But because they are thinking in the worst case scenarios, they're always thinking in the opposite. What is the minimum that I can take and what's the maximum that I have to give? And the pruning, which is the termination of the recursive call, so if you remember the minimax was a recursive call, it will happen when the value of the current node, so the node will have a value, a current value. And if that value is worse than the current alpha and beta value, or beta value, depending on the player, then you can stop going to those nodes. So you're not going to call the function on these nodes that should not be explored. Okay, before I show you a walkthrough of this algorithm, this is the pseudocode that is in the textbook. So what you will see is there are two main functions, max value and min value, which are tied to max and min, okay? And what you will notice, a bit of difference to Minimax, it has three parameters. I think Minimax only took the state, but alpha beta takes two values, alpha and beta, okay, that I've mentioned just now. And this function will return a value. So it takes three parameters, which is the state, alpha. Alpha actually represents the highest or the best already explored option for max from root to the current node. And beta represents the lowest value or the best value for the minimum, for min, from root to x. And the third parameter that's to do with this function is a v value, a value which is the value of the node, and this value will be returned. Okay, this is an output function, output value. So the function will always return v, but will always take in alpha and beta. And at the start node, so when this algorithm starts, it's going to initialize alpha to minus infinity. Now, why is that? Alpha is a maximizing node, okay? It's tied to max. So in order to get alpha, to get max, to even play the game, you start off by telling alpha, okay, the minimum that you can take is actually minus infinity. Okay, so you can take minus infinity. So you're saying, oh, that's really bad, meaning a very, very, very small number. And by saying, okay, this is what you can take, then you're saying, okay, then I actually have to play this game and I have to at least take the first path in this game tree because it seems like I have a very small default value, right? This is just like a default value. So it has a very, very small value. And for beta, it's the exact opposite, because beta is a minimizer node tied to min. You say, okay, this is kind of how much you have to give at the beginning. And it turns out that you give beta a very big value, like, plus infinity. So beta says, oh, well, this seems really bad, right? I'm never going to win this game unless I play it. So I better play this game. So I might actually have to give less than, infinity. So this is the rationale for initializing these values to minus infinity and plus infinity. And as the algorithm goes, okay, we're going to see a lot of subtle things. Alpha and beta will be tracked, okay, as globally at the high level and locally at the node level, okay, and they will always be keeping track of upper and lower bounds of these values, just as we spoke about when we looked at that example where we could prune parts of the tree. And v is then the value that is used to manipulate alpha and beta, and it is passed back from the function. Okay, at the moment you got a little bit more insight to this to the algorithm, but you still don't have a full technical breakdown of it. So the next page is going to be very important. Let's look at it. Okay, so here is a walkthrough. This is the most important slide of this lecture, so please pay attention for the next, I don't know how long it's going to take me to explain it to you. So I have just rewritten that function just now. Okay, it's exactly the same. I've just changed it to have one function call. If you look here, it's calling max value, and then max value calls min value. I just wanted to rename that to minimax alpha beta. I just called it minimax AB, and I just have one function, and in that function you're just going to check. So it's the same. I've just rewritten it with very small minimal way. Okay, if you're more comfortable with this, feel free to work with this. Okay, but I'm going to work with this for now. And I have taken the example from the textbook, which is exactly the example we looked at just now, just to show a very, supposedly simple, but not so simple demonstration. So we start off with our function alpha beta, and we start at the root. So we just initialize S to be the root node, okay? And then we're going to return a value because minimax AB or alpha beta pruning should return a value, and that's going to be our V. So we start off with the root node, and we call it passing the root node and the initial values for alpha and beta. Remember we said alpha gets minus infinity and beta gets plus infinity. So those values are passed at the first call. And so let's step through this. So at the root, okay, we have the values in the square brackets are values of alpha and beta. Okay, everywhere you see it's the value of alpha and beta. So alpha first followed by beta. So we're in here, okay, we've called the function, we are in here, state roots, alpha is minus infinity, beta is plus infinity, and we're going to do the first terminal test. So we're going to check whether this is a terminal node. Turns out it's not, so we can't do the base case. So then we're going to check, is the player max? And at this point, this is max. So yes, we are max, okay? And the first thing we're going to do is we're going to have this variable v, which we spoke about, is going to get the value minus infinity, okay? So because we're at a max value, we're at a max node, v is going to get minus infinity, okay? Remember there's v, there's alpha, and beta. There are three variables that we're dealing with. And now we're going to see for each child of our node of S, which is at present A, we're going to run this algorithm again. We're going to say that V is the max, okay, of V, which is at the moment minus infinity and the minimax AB of the first child. So we're doing this for every child. So first we're going to just look at B. Okay, so it's the minimax AB of B with the values of alpha and beta, which I didn't bother to write here because you can see them here. Okay, so far so good. And so we go to the first child, and when we are calling this, so we have to go back to the beginning of our function. Okay, so now we're back here for this state here. So we call function minimax AB. Right now, the state is our new state, which is the child state B, and alpha and beta will still have the value as before, minus infinity and plus infinity. And we're going to have to, again, we're going to have to do this terminal test. Okay, B is not a terminal test. And then we're going to check, is it a max player? It's not. Then it's going to check, is it a min player? Then yes, it is. So let's go into this line of code, into this chunk of code, and we see that at B, we're going to initialize V to plus infinity. Okay, so now we're at this level, and we just follow the algorithm. V is plus infinity. And now we're going to, in turn, look at every child of B. Okay, because this is depth first search. This is how depth first search works. So if you didn't get it the first time, you probably will get it now. So for each child C of S, V is now going to have the minimum, okay, the minimum of V between V, which is plus infinity, and the minimax of the first child. And in this case, I just called it 3. I didn't want to give it another name, okay? So we have to call minimax AB on this node now. So we have to go back up, okay, back to this, and this time the state is this node, and alpha and beta are passed as minus and plus infinity. And we're going to do this test. Is this a terminal node? And turns out that this is a terminal node. So what we're going to do is we're just going to return the utility value, okay? If you notice, earlier there were just recursive calls. This one was calling itself. This one was calling itself onto its child node, onto its child node. But now we're already at the leaf node. So it will not go into any of these guys, but it will just be here. It says it is a terminal test, so then just return the utility. Now remember, return means you are exiting the function. You are not continuing, right? The return statement means you are getting out of there and you're returning a value. Okay, so here it's going to return 3. Okay, so that value, V, gets propagated up back to its parent or back to the calling function just now, okay, where we saw was back down here, right, where it was actually called. So now we have a value, okay, and that value is 3. Okay, that value 3 has been passed, and now we can calculate this expression here. Okay, the minimum between plus infinity and 3. And the minimum between plus infinity and 3 is obviously going to be 3. Okay, and we have to assign that value to V. So now V gets updated with the value 3. Okay, so we're done with this part so far for this particular child of B. Now let's get to the next stage of this code. So we're done with that child, and we're going to check at every single child if V is smaller than alpha. Okay, V just got assigned the value 3, and alpha is minus infinity. And we're going to check now, is V smaller than or equal to alpha? Well, it's not. Okay, so it's not. It's bigger than alpha because alpha is minus infinity. So we're not going to do this. We're actually just going to go to the next line of code. So since V is not smaller than alpha, then we're going to do something to beta. Beta now, which is plus infinity here, is going to get the minimum between the current beta, which is just plus infinity, and V. So between plus infinity and 3, it's obvious that 3 is the smaller value. So now beta gets updated. So now we have alpha, which is still minus infinity, but now beta is plus 3. Okay? And we're done with this chunk of code for this one child. So we have to repeat that for the next children. Okay? So now we go to the next child. So we start off where at this stage v is 3, still 3, okay, because it's been updated just now. And we go down to this child. We call this function, okay. V is now the minimum between v and the minimax of the next child. So v is now 3 and minimax of this node called 12. So we will just return the value 12 because this is a leave node, and it's just going to return the utility value. And now we can fill in the gap, and we can say v is going to get the minimum value between 3 and 12, and that is just going to be 3 again because 12 is bigger than 3. So nothing happens to v. V remains 3, okay. It's also going to do this checks, okay, with alpha and beta, but nothing is going to change because v hasn't, nothing has happened to v, so this is not going to change either, okay. So now the next step is it would have done the third node, okay, and it turns out that 8 is also not smaller than 3. So nothing changes. So we have v, which was 3 now, pass back up, okay, because you're done with all the children, and these are the values that you have for v and alpha and beta, okay, and v is passed back, okay. Alpha and beta they're not passed back, okay, they're just been used here. And just v is passed back, which is 3. And now we're back at a. Okay, we're back at a, which was the max player, because initially we had called this function on the first child. So now, since we've called it on the first child, we then have to check whether v is bigger than beta. Now remember, v of our node here is actually minus infinity, right? That's why I have it in purple. This is the copy of the variables at alpha, okay? They remain at max, okay? Even though in min here things change, the only thing that max gets back now is the value of v, okay? And basically it initially called with the max of the initial value of v, which was minus infinity, okay, that was what it had, and the value that was returned from the minimax AB called to its child. It turns out that this value was 3 just now. So now v will be the maximum between these two values, and that is 3. Okay, so now v gets the value 3. Okay, and then it goes on to do this. It's going to check if v is bigger than or equal to beta. Beta here is plus infinity, so it's not, okay, so we don't go there. And then we're going to check if alpha, then alpha is going to be the maximum between alpha and v. So alpha here is minus infinity and v is 3, so obviously v is bigger, so alpha gets updated. Okay, so alpha got updated and it became 3 now, okay, as a result of this. And now it has to go to its next child, okay, so now we're back up to max, okay, and so it's going to call this function again, and it's going to now call max, okay, of v which is now 3, and the minimax AB of c. So it's going to repeat what it did to this B node, but with C. So alpha and beta get passed down, okay, 3 and plus infinity get passed down. Now V will be reset, okay, V will be reset to plus infinity every time it gets to a node, for a minimal node. And then for every child of C, it's going to do something. So first it's going to check, it's going to call this value, okay? It's going to give V the value of the minimum between V and minimax of the first child. So in this case, the first child is 2. And since 2 is a leaf node, it's going to return the value 2, and you're going to get that you have to evaluate the minimum between plus infinity and 2. So the minimum between plus infinity and 2 is 2, okay? So V gets updated to 2. So we're done with this part here. Let's go to the next line of code. Now this is an important part. So we're doing this check. We check if V is smaller than or equal to alpha. So alpha now has the value 3, right? It was inherited from the parent just now. So V has the value of 2. And therefore this, this statement passes. It passes this statement and it goes in. So since that has happened, since V is smaller than alpha, 2 is smaller than 3, we're just going to return V now back up. Okay? So that means we're doing the pruning. We're not going to investigate the remaining children, okay? Because this return statement, actually, as I told you, return statement is just going to exit the function, right? So it's just returning V altogether. So it's returning the value 2 back up. And, it's not going to go back to this for loop because return means get out of the function, exit, yeah? And you are returning V, which at the moment holds the value 2. And this is where pruning happens because these two children are not visited, okay? You're now going back and we've returned it back to max, okay? So V is just returned back to max, and now max gets 2 up there, right? It gets the second value because this result now is 2, right? Remember, this was the result of that minimax AB2, minimax ABC, okay? And now max will continue processing the next line of code, which says, okay, note that V first gets the value 2, okay? Oops. Okay, I should update V with 2 there, okay? Sorry, no, V just stays 3, obviously, okay? Because 3 is bigger than 2, okay? And nothing happens to V. V remains 3, and then it's going to check if V is bigger than or equal to beta, and it's not, okay, because beta is plus infinity and V is just 3, so it doesn't do that. Else alpha is going to be the max between alpha and V. So since V is 3 and alpha is 3, nothing happens. So max doesn't, alpha doesn't get updated, okay? So the main thing here is we ignored this portion of the tree. Exactly using the same intuition that we saw earlier on, but this time we are following the algorithm, which guarantees that we can do this in a computation way, right? So we move on, right? We move on and we move on to the next stage now that alpha, that max now processes the next child, okay, which is D. And V now still has the value 3. And max will call minimax on the child D. And it has to see which is the max between V and the minimax of that child. And so it goes there, and alpha and beta pass down, okay, as 3 and plus infinity. And it goes to the first child, which happens to be 14. and v has been set to plus infinity, and we will call, because this is a minimizing node, so it's going to call the minimum of plus infinity and the minimax of that child, which is 14, and it will just return the value 14, and we're going to get the minimum value between plus infinity and 14, which is just 14. So v will get that value, right? And then we're going to check, is v smaller than or equal to alpha? Oh, it's not, it's bigger. So we're not going to do that. And then we're going to check beta. Beta is going to be the minimum between the current value of beta and 14. So we will see that yes, indeed, beta will have to take the value 14 because 14 is smaller than plus infinity. Okay, so beta has been updated, and it goes on to the next child. Okay, so it will just go on to the next child, and it will go to 5, and it will come back and say, because v is now 14, and v will be updated to get the value 5 because 5 is smaller than 14, and beta gets updated to 5, right? And finally it goes to this node and it sees that it's 2, and 2 is also smaller than 5 just now, so it's v is going to get the value of 2, okay? And beta will be updated to 2 as well, right? As with the same logic. And finally, since we're done with all the children, it's just going to return v, okay? And v is 2 in this case because it has processed all 3 nodes, and it found that v is 2, and 2 is passed back up to the root node, and root node is going to check, right? Root node is going to check which is the max between 3, which was the original value here, and minimax AB of D, which was 2 just now, and it's just going to be 3, right? And it's going to do this check, okay, is V bigger than or equal to beta? It's not. Alpha is going to be the max between alpha and V, so it's done. And then it returns v, okay? So at the moment, v is 3, okay? So when it's done with all that and done with all its children, it goes down to the return statement and it returns v. So v here is just 3, and when you pass 3 back to, the highest level where it's called, v has the value 3 now, and then it's basically going to return the action. It's going to say, okay, Max, you have to take the action with the value 3, and that action is actually B. I didn't actually put these these values from before because the diagram was going to get too crowded otherwise. So basically, alpha beta pruning says, okay, you have to take this one here to give you the best outcome for this game. Okay, so that is a walkthrough of alpha beta. Now, I do not expect you to get it right away, but those of you who are very analytical, those of you who can follow step-by-step algorithm, if you just follow the algorithm, you'll be able to get it, right? However, you also, at the first instance, you need to understand the intuition. You need to understand what is going on, which, we already spoke about earlier in this lecture, about, why we want to trim out certain parts of the tree. And if you can intuitively get your head around it, and then if you can figure out how the algorithm is doing that, and then you're done, right? So let's think about a few points that I can just give you right now. So talk about these 3 variables, okay? Alpha and beta, okay, they are actually inherited, right? As you're going down the tree, the game tree, alpha and beta are inherited. So if you are a node, you get your alpha and beta value from your parent. However, once you have your alpha and beta, you're going to play around with it, right? You're going to change it, as we saw. Alpha was changed, beta was changed. But this value of alpha and beta are not passed back up to the parent. So the parent will not get back that alpha and beta value. It's just inherited, but they are used for a node's own use, and they are not passed back up. The only thing that's passed back up is V, right? Because if you look at here, all these return statements, you will only see V. Okay, utility here, here it's returning V, here it's returning V, and here it's returning V. So only V is passed back up. Okay, alpha and beta are used for processing. And that is one important thing that helps you understand the algorithm. And then the next thing to understand is every time you go to a node, okay, the V value, the value of V is reset. Okay, it's reset to minus infinity if that's a maximizing node, if it's a max player, or it's reset to plus infinity if it's a min player. Okay, so these two things are very important. You inherit the alpha and beta, and every time you're at that node, your V value is reset to plus or minus infinity. And then at max, the next thing you need to figure out is pruning. So pruning happens, okay, meaning you're going to ignore parts of the tree when V is bigger than beta. When you're at a maximizing node and V is bigger than beta. That's because the min player above you, okay, before you, will ignore this path because it is worse, okay? It is worse for that min player to take this option because this particular value, V, is bigger than the best minimum value that they have, which is beta. Okay, that is the kind of logic behind it. Okay, if you don't look at the math, but that's the explanation of the math. And if you're at a min node, pruning happens when V is smaller than alpha. Okay, and what that means is the max player before the min or above will ignore this path because this V value is worse or it is smaller than the best that they have so far, okay, which is alpha. So the alpha that they have is bigger than, the option that you have right now. And this is basically the whole, the holy grail of it. So I don't expect you to get all of this right away. Of course, if you do, fantastic. Maybe you're familiar with all this already or you're very algorithmic minded. So don't worry about it. Take it step by step. We will meet again and probably in a live class, and we can work through an exercise. So to get, everyone to get working on this algorithm. And just to finish off, okay, pruning does not affect the final result, right, as we've seen. And also when we've seen just now, when we put the ordering of the moves, right, we had 14, 5, and 2. So we had to actually look at all those, the last node that had 14, 5, and 2. If we actually, since we had 14, we had to look at all the 3 nodes. But if we had 2 here, we could have pruned that node already. We could have pruned the other 2, right? So the ordering of those moves can improve the effectiveness, okay? And it turns out with this kind of perfect ordering, the time complexity is now reduced to or b to the power of m over 2. Okay, so this is really good because it's much smaller than what we had earlier, and it can get to imagine like it can actually play chess pretty well as opposed to waiting for b to the power of m. Okay, so I hope I better stop over there. I let you work on your own, and I'll see you next time.